settle this over a pint? No. All right, then. Come on!
Shrek. Most of us have seen it, and most of us love it. This 2001 blockbuster reached booming success with its original plot, dynamic characters, and witty humor. But is it just the characters in the movie that are from fairy tales? Or are the physical bounds of this world the result of movie magic as well? Let's take a look at the first scene in the movie, in which Shrek slams open an outhouse door.
Yeah. Like that's ever gonna happen. What a load of...
Somebody once told me the world.
Shrek slams the door open at an incredible speed, which means he must have applied a pretty big force to the door. So the question we're asking is, should the door have broken under such a large impulse? Let's take a closer look and add some math in there to find out.
What a load of...
Somebody.
After some extensive research, we decided that Shrek is most likely 8 feet tall, which is about 2.5 meters. Using this scale, we determined that the door to the outhouse is about 1.25 meters wide. Now we need to find the angular acceleration of the door as Shrek opens it. To do this, we'll use the frame rate of the movie. We know this movie runs at 24 frames per second, which means one frame is 1/24 of a second, so we just have to count how many frames it takes Shrek to open the door. 1, 2, 3, 4, 5, 6. It takes Shrek 6 frames to open the door from a position of 0 degrees to a position of 180 degrees, or 2 pi radians. If it took the door 6 frames to go from 0 to 2 pi radians, that means it took 1/4 of a second. Using this, we can find the angular acceleration of the door to be 8 radians per second squared. We also found out that the most common tree in swamplands is the red oak. The door is about 8 feet high and 4.1 feet wide, and we're estimating about 1 inch thick, which means the door weighs about 44 kilograms. For our calculations, we'll assume Shrek applies a force perpendicular to the door that's about 1 meter away from the pivot point. Using all this information, the 2 torque equations that we know, and the moment of inertia for a rectangular plane spun about one end, we can figure out that the force Shrek applied to the door is equal to about 183 newtons. Now, just to put this in perspective, a force of 183 newtons is the same as the force you would feel if a 10-kilogram mass was hurled at you going 91 meters per second, or a 22-pound weight hitting you at a speed of 203 miles per hour. Now we will demonstrate this, but on a much smaller scale, since such speeds would be difficult to reach at home. We'll be using a plank of white pine, which has a bending strength a little greater than half that of red oak, as well as a 4.5 kilogram mass, since it will be traveling at a slower speed as well.
Okay, ready?
Ready.
Good.
The wood broke, which isn't really a surprise, but now we can say with confidence that the door should have broken in the movie. 1 down, 1 to go.
What?
Now let's take a look at a scene later on in the movie, when Shrek and Donkey are crossing a bridge to the castle to save Fiona, which later has broken in half and all 3 are hanging onto for dear life.
Really?
Really.
Okay. That makes me feel so much better.
Just keep moving. And don't look down.
Okay. Look down. Look down. Keep on moving. Don't look down. Don't look down. Keep on moving and don't look down. Shrek! I'm looking down! Oh, God, I can't do this. Just let me off right now, please.
If the bridge was already on the verge of breaking with Shrek and Donkey on it, then would it really have been able to hold up Shrek, Donkey, and Fiona later on in the scene? Or should our heroes really have fallen to their death in the lava below? Let's take a closer look to find out. Firstly, let's assume that when Shrek and Donkey are in the middle of the bridge, both sides of the bridge are at their maximum tension. Here's our diagram for the situation. After some more research, we have decided Shrek has a mass of 181 kilograms and Donkey has a mass of 113 kilograms, giving them a total mass of 294 kilograms. In order to simplify calculations, we will assume that when Shrek and Donkey are in the middle of the bridge, it is bent at a 20-degree angle. Here's the free body diagram of the situation. As you can see, the weight of Shrek and Donkey is equal to twice the maximum tension times the sine of 20 degrees. So with a little derivation, we can find that the maximum tension in the rope is equal to about 4,212 newtons. Now let's see if the other end of this scene holds up to these calculations. Here we have a diagram of the situation after the bridge breaks. We'll assume that Fiona has a mass of 59 kilograms. In this free body diagram, we can see that the largest tension in the chain is at the top, and this section has to hold up all three characters. To find this tension, we simply take the total mass of the three heroes and multiply it by their acceleration due to gravity, which gives us a tension of 3,459 newtons. So since this tension is less than the maximum tension of the ropes, they really wouldn't have fallen after all. Well, I hope this all wasn't too overwhelming, but that's the end of our physical analysis of the movie Shrek. Thanks for watching.